Video problem number 97, electrical energy from oxidation reduction reactions. We are going to draw the voltaic cell. Alright, so first of all what we have to do is figure out what's being oxidized, what's being reduced. In this case, I have the complete reaction. If I want to, I can sort of break this down into the net ionic, which is going to be zinc solid plus protons yields zinc 2 plus hydrogen. Obviously I have to balance it. Oh, why did I put a 2 in front of that? Should be in 2 in front of that. That should be balanced. Okay, so now it's mass and charge balance. So now I can see my zinc is going from 0 to positive 2. My hydrogen is going from positive 1 to 0. Right? So 0 to positive 2, what is that? Well, that is losing electrons, so zinc is being oxidized. Right? So let's just jot this down here real quick, make some notes. Zinc is being oxidized. Okay. That must mean that the proton is being reduced. Okay, so now we can start to draw our voltaic cell. So what we're going to do is draw one beaker, and then draw a second beaker, put some solution into each beaker. We're going to label the beaker on the left as the anode, the beaker on the right as the cathode. All right. Now, oxidation occurs at the anode. That means that I'm going to put that oxidation reaction into the anode. So, the solution then must be made of zinc chloride. So let's give that solution of zinc chloride in there. Okay. Now I need an electrode. I need a chunk of metal that I'm going to be able to hook a wire up to. Zinc is a pretty common metal, so I'm going to use zinc as my metal. So there's my electrode. Okay? Now that must mean that the hydrogen ion is being oxidized. Right? So let's put the solution of hydrogen ion in here. If we want to, we can make it HCl. We did with the other one, so let's go ahead and make it HCl. And then we're also going to have hydrogen bubbles, right? Because it's forming hydrogen gas. So let's do that. All right. Now notice there's not a metal in the reduction reaction. Okay. Let's label this. Whatever is being reduced is occurring at the cathode. Okay, there isn't a metal, so that means we need to use an inert metal. So I'm going to throw an electrode in there. Now, I can use either carbon, graphite. So that one's pretty good, and that one works well, especially if you don't have a ton of money. Or you can use platinum if you're rich. Right? So there I have each of my half reactions. I have the anode, which is the site of oxidation. I have the cathode, which is the site of reduction. Now what I need to do is attach these two with a wire. So there's a wire, right? And the electrons travel along the wire. So let's write the electrons up here. Okay, now let's indicate which way they flow. Electrons always flow alphabetically from anode to cathode along the wire. Okay, now if I had just this, the voltaic cell, the battery, would end quick. Alright, because I'm getting more and more negative in the cathode, more and more positive in the anode. So what I need to do is I need to put in what's called a salt bridge. Okay, so this is my salt bridge. And the salt bridge allows an ionic compound that's not going to react to travel. So we're going to use sodium nitrate for our salt bridge. Okay, now the sodium ion goes through the salt bridge, through this tube, but it goes into the cathode. The cation goes to the cathode. The anion goes to the anode, and that's to balance out the charge. Remember, the cathode gaining the electrons, becoming more and more negative, so I need to put something positive in there to balance out the negative charge. The nitrate, because the anode is becoming more and more positive as it loses electrons, so the nitrate's there to balance out the charge. Let's try another one. Okay, so this one's already in the net ionic. So let's see. I am what's going on here? I've got the oxygen, which is a -2. So manganese has to be +7, and over here it's positive 2. So from that alone, I can figure out what's happening. That is gaining electrons, right? So that must mean that's being reduced. So the permanganate, MnO4 minus, going to manganese. That's being reduced. That must mean that the chloride going to HClO is being oxidized. Okay, so now I can draw my beakers. Beaker 1, ooh, that was big. Beaker 2, draw solutions for both of them. Alright, label one of them the anode, the other one the cathode. Okay. So remember, what's being reduced occurs at the cathode, and I remember that the way that I use it is that's a consonant, that's a consonant. So they both start with consonants. What's being oxidized occurs at the anode, val. Right. So what's in the anode? Well, I've got the chloride solution, and I have HClO. Again, I don't have a solid metal, so I'm going to use, in this case, carbon graphite. Alright, so look at the cathode now. We've got permanganate, we got manganese, and you might want to go ahead and balance these to see if you need protons in there as well. Okay, we're just sort of doing a, yeah, I'll do it here in a second. Alright, so again, no metal, so let's go with carbon graphite. I got a wire connecting these two, and I got a salt bridge. Okay, electrons always flow from anode to cathode. Alright, and if I use sodium nitrate again, the anion goes to the anode, the cation goes to the cathode. Now I mentioned we might want to look at this balanced reaction, so let's go ahead and do that. Give me 1 second, I'll be back with it. Alright, so here's our answer. This is our answer from 94A, so you can sort of flip back and see. So let's see, what else do we need? We do need some protons in a couple of places, right? We need protons in the chloride beaker, so let's put some protons in there. In other words, we need some acid in there for this reaction to happen, right? And then it looks like we also need some hydrogen ions in the cathode as well. So let's put some acid in there as well, because we need that for the reaction to actually occur. Okay, so make sure that you're using the balanced redox reaction and not just what you're given. Now, of course, we can couple this with video problem number 96, and we can actually figure out the voltage of each one of these. So